So good evening students, can you all hear me? And can you all see the screen clearly? So please respond, please do type in the chat box. So can you all hear me? And can you all see the screen? Yes? Yeah, good evening Kapil. And good evening every one of you. So please respond, please type in the chat box. Okay, fine. So if you quickly recollect, this is our fourth lecture on this first module, fluid and its properties. Yeah, you all can hear me, correct? Good. So this is our fourth lecture on this topic, fluid and its properties basically, correct? So in first three lectures, we have seen what is the basic discrimination between a solid and a fluid, correct? And then after we have seen this concept of viscosity and Newton's law of viscosity as well. And of course, in yesterday's class, we have seen what are different classification of fluids depending upon the Ostwald-Wallis model, correct? So these are the things that are with us. So in today's class, basically we deal with some cases of viscosity. So various cases of viscosity, of course, which a couple of cases we have dealt in yesterday's class, like basically pulling a plate at constant velocity between a horizontal gap, and also we have seen a shaft rotating inside a journal, correct? So these are the two things that we have seen. So in today's class, we will extend this various Newton's laws of various cases of this Newton's laws of viscosity, and also we move on to a bit of basics on compressibility as well. So are you all clear till here? So are you all clear with the past three lectures that happened here? Yes? So please do type in the chat box. Are you all clear with the past three lectures here? Just a second, guys. Okay, fine. Yes. So today we'll start about we'll continue basically the other laws of viscosity as well. Okay. So the other cases of Newton's laws of viscosity. So let us suppose there is some inclined plane. Okay. So let us suppose there is some inclined plane which is inclined to the horizontal at an angle of theta, and let us suppose there is one horizontal block on this. So let us suppose there is one horizontal block on this. Okay. So there is one horizontal block on this particular plane. Okay, and let us suppose this horizontal block is at a height h from the plane, and of course the gap in between these two is filled with some viscous oil. Let us suppose this is your viscous oil that is in between here. Okay, so let us suppose this is some viscous oil that is in between the plane and the box that is sliding on this plane, or basically on this wedge respectively. So now if you try to identify different forces that are acting on this block, if you try to identify, first of all, the weight is something, or else if you draw the free body diagram of this block which is of weight W, if you try to draw the free body diagram of this block, look carefully, we'll try to draw one free body diagram as well. Okay, so let us try to draw one free body diagram of this block which is acting, which is falling on this inclined plane. So basically this block, if you write the forces that are acting on this block, there is weight that acts vertically in the downward direction, and of course whenever this block, let us suppose this is the direction in which this block is sliding with a uniform velocity v. So if this is the direction in which the block is sliding, then definitely the shear force due to this viscousness of the fluid will act in the opposite direction, correct? So let us suppose this is your direction of the viscous force that's acting away. Okay, so this is your viscous force Fv, and under the action of these two forces, of course weight will be acting vertically downwards, and there is some viscous force that's acting at an angle which is perpendicular to the which an angle which is equal to the theta, because this angle between this horizontal and this Fv is nothing but the angle between this along this inclined plane and also this horizontal, correct? So that's what we know. So if you apply the static equilibrium of this block, because let us suppose this v is the terminal velocity, means this is a constant velocity. Okay, so this is your terminal velocity, which means the block is moving at some constant velocity. Now from your mechanics point of view, you know, if a block is moving at some constant velocity, then the net force acting on the block is zero, correct? Which means whenever this block is falling with some uniform velocity, the net effect of these forces on this block is zero, which we know this means at least along this plane. So if you resolve this force along this plane, then you know, if you resolve this W, then you know there is some component of W that acting in this direction, which is given by W sine theta, and of course this component which is perpendicular to this will act along this, and this component is nothing but W cos theta, correct? So this is W cos theta, and of course this is your W sin theta, that's what it's acting. And now if you try to apply the equilibrium along this plane of this inclination, then this W sin theta which is here should be equal to, yes, W sin theta and W cos theta, correct? So now this W sin theta should be equal to this FW, because this block is not experiencing any acceleration in this inclination direction, correct? So this block is moving with some terminal velocity, which means this block is not experiencing any acceleration. That means this W sin theta force, which is due to the weight of this block, should be contradicting this viscous force which is acting here. Good evening, Nikhil. So see here, if you write Fv is equal to W sin theta, if you write Fv is equal to this W sin theta, so this implies what is your viscous force now? Viscous force is nothing but can be written as shear stress that's acting on the block into area that's in contact. And let us suppose in the top view, if you look, let us suppose capital A is the area in contact. So let us suppose area A is in contact. Area is in contact with fluid. Area A is in contact with fluid. Then you can clearly understand that tau s into A will give you the shear force that's acting on this fluid, I mean this block, because of this fluid. So this is equal to W times of sin theta, correct? So this is W times of sin theta, and shear stress acting can be identified by Newton's law of viscosity. And let us suppose this clearance is so small. Okay, so if that clearance is very much small, then you can approximate your velocity profile to be linear, correct? Let us use this color. So if you see, your velocity profile on this block is linear. Okay, so let us draw it this way because the block is moving in this way. So you can see this velocity vectors increases slowly, correct? So basically this is your velocity profile, and this tau s can be written as, if this clearance is denoted by h, if this clearance is denoted by h, then tau s can be written by mu of this liquid, means the dynamic viscosity of this liquid, into velocity gradient. And velocity gradient perpendicular to the direction of the plane is nothing but, here the fluid velocity is 0 because of the no slip condition, and here the block is moving with a velocity v, which means the fluid layer which is in contact with the block is also moving at some velocity v. So this can be written as v divided by the clearance h, which we have written here, into area. This is equal to W sin theta. So if you write the formula for terminal velocity of the block, this implies v is equal to WH sin theta, WH sin theta divided by mu times of area in contact with the shear. And this is a very important gate question, and that came many of the times here. Okay, so basically when a block is sliding along this plane, then without any external force that's acting except the weight and the viscous forces, then the velocity, the terminal velocity attained by the block is this. Means after this velocity there won't be any acceleration of the block, and the block starts moving with uniform velocity. Clear? This is a simple analysis which you can easily see. There is some block basically. So along this plane there is some viscous force which is offered by the viscosity of this fluid that is in touch with the solid, and of course the weight of the solid is acting vertically, vertically downwards, and a component of this vertical weight acts along the plane. So are you all clear till this point? This is a simple resolution of forces basically. Clear? Yes? Are you all clear till this point? Generally it's given in degrees. Okay, so sine 30 degrees, 15 degrees, this inclination theta is generally given in degrees, so no issue. So while solving the problems, you can substitute this theta always in degrees. Is that clear to all of you? So here is on live, so please do respond. Are you all clear till this point? Now in some cases, yes, very good. So here what are the cases that we have seen? For example, in shaft and journal oils, it is block sliding. In all these cases, the points of fluid and solid contact are equidistant from the references, but there are few cases where your points of fluid and solid contact are not at equidistance from some reference. For example, look here, I'll tell you how they appear to be. So let us suppose there is some, where is this going? Okay, fine. So let us suppose there is some disc, okay, and this disc is surrounded by some fluid. Let us suppose this disc is mounted on some fluid. This disc is mounted upon by some fluid. Okay, fine. So let us suppose these are the things that are with us, and yes, so this is the disc. Okay, and this disc is rotated about its midplane. Okay, so fine. Let us suppose we are trying to draw one disc, and this disc is rotated about its midplane. Okay, so similarly, now if you try to look at the top view of this, basically there is one disc which is sitting on this, and there is some viscous oil in between. You can observe the viscous oil somewhere here. So this is the viscous oil that is present, okay, between the disc and the fixed surface. So this is some viscous fluid that is located between the disc and the viscous fluid. Okay, so let us suppose this is the case. Then if you try to draw the top view of this disc, see carefully, we are trying to attempt this. Okay, and we have one more line that we can plot here. Fine. So let us suppose we are trying to plot the top view of this disc. Okay, let me try to plot that. The disc we have taken in wet color, so even this we have, which we can take this in wet color a bit. Okay, fine. So let us suppose this is the disc that is with us in the top view. Okay, and let us suppose now, if you see carefully the basic difference between this diagram and the previous diagrams. Now, in previous diagrams, in case of journal and shaft, or in case of plate moving in between the horizontal gap or something, then the points of fluid and solid contact are at equidistant from reference. But if your shaft is means if your disc is rotating at some angular velocity omega here, then this complete disc is rotating about this axis, but you see clearly this all are the points of contact between the solid and the fluid. You can see clearly these are the points of contact between the solid and fluid. Are these complete points at a fixed distance from this axis of rotation? Please tell me, are these complete points at a fixed distance from this axis of rotation? Please try to observe the difference, friends. In previous places of journal and shaft and also a plate moving in a horizontal gap, all the points of fluid solid contact are at equidistant from reference. But now if you take this as a reference, now are these points at equidistant about this reference rotating axis? No, they are not in a fixed distance, correct? Because you see this point is at a distance of some radius from this. Again, this point is at a bit of more radius from this. Finally, the point which is here is at a large distance from this, correct? So they are not at a fixed distance. So in such cases, what we do? Look, to analyze such situations, let us suppose this is a viscous fluid and the gap in between this means basically this clearance is, let us suppose this clearance is very small h, then we can assume a linear velocity profile within the oil. So if you assume a linear velocity profile within the oil, so let us suppose I am assuming some linear velocity profile within the oil. Okay, so if the disc is rotating, similarly here. Fine. So let us suppose this distance which we are taking is small r for the time being. Okay, and if you take this distance as the small r, then see carefully, I am trying to plot this. Okay, and let us suppose at some equidistantly we are taking one more reference axis. Okay, fine. So now let us suppose we are trying to have a circle concentrically with this, and of course this is again somewhere here fitting in between this, correct? So this is a concentric circle which is corresponding to this section, means when you look at this disc from the top view, we will see a circle which is at a distance smaller, correct? So this distance from the center which you are measuring is small r. Okay, so to analyze this situation, let us take a strip on this disc of thickness dr. So let me take one more strip. Let us take one more strip. Okay, so this is one elemental strip which is at a thickness dr from this r. Okay, so basically this thickness which you are having here is dr. So can you all imagine this diagram clearly? First of all, there is a disc that's getting rotated on the top of a viscous oil, and now if you are looking at the top view of this disc, if you see the top view of this disc, then this complete area is in contact with the oil. So since all the points of this solid fluid contact are at not equal distance from the oil, so I can't apply the simple formulas. I need to go for elemental areas. So now, if I am taking a strip which is at a radius of r and thickness dr, then can you imagine that this small area is look carefully, this small area which is here is in contact with the fluid, correct? Yes or no? Correct? Can you all identify that this small area on the disc is in contact with the fluid? Yes or no? And if this radius is smaller, can you tell me what is the linear velocity at this point? If this is smaller and if this disk is rotating at an angular speed of omega, then the linear velocity at this location is r times of omega, correct? So v is equal to r times of omega, and of course this is at a distance smaller from the center. Now, if you apply the Newton's law of viscosity here, your tau is equal to, or d tau, maybe small shear stress that's acting on this elemental area is equal to mu into dynamic viscosity of the aisle, which is fixed. So linear velocity variation within here. See, the velocity of this point will be something less than as compared to this point because the radius is increasing, correct? So r omega divided by this clearance between the disk and the plate is h. So rw divided by h. R omega divided by h. So this is the small shear stress that's acting on this elemental area. Now, if I denote this shaded area with dA, can you tell me what is the value of this dA? Can you tell me what is the value of this dA? Any one of you. Can you tell me what is the value of this small elemental area dA? Anyone? This is the elemental area that is at a radius r and of thickness dr. Because linear velocity is equal to radius vector into the angular velocity. So can you please tell me what is this elemental area dA that we have hatched here? So that small area dA is nothing but 2 pi r into dr. How this is 2 pi r into dr? Because you know this elemental area can be taken as this outer circle area minus this inner circle area, correct? And what is the radius of the outer circle? This is actually identified from, look, I will give you the complete idea of this. Initially, if you take the outer circle area, we have pi into r plus dr whole square minus pi r square, correct? Because the inner circle area is pi r square and the outer circle area is pi times of r plus dr whole square. So this is equal to pi times of r square plus 2r dr into dr square. Plus dr whole square minus pi r square. So you can see clearly this r square and this pi r square term gets cancelled because of a multiplication of pi. And if you neglect higher order terms, because dr thickness is very small, so dr whole square can be neglected very easily, correct? So if you are neglecting this term, then this small elemental area that's coming here is dA is equal to 2 pi r dr. Okay, because this question is also very familiar in many of the exams, so I am just discussing this. So if you have a disk on the top of any solid that is fixed, of course this plate is fixed actually, so you can identify that this plate is fixed now. So if this plate is fixed, then definitely when this clearance is h and if the disk is rotating at some angular velocity omega, then if this is the analysis that you are carrying out, then the shear force, that means the small shear force that's acting, dF is equal to the shear stress into area, correct? D tau into dA. This is nothing but mu into r omega by h into 2 pi r dr. So this is the elemental force that's acting on this elemental strip. Are you all clear till this point? Can you all identify why this small force acting is nothing but the small shear stress that's acting on this block into dA? So mu into at this particular point which is at a distance of r from the axis of rotation, then the linear velocity of the particle here is r times of omega. So r times of omega divided by this clearance is nothing but the velocity gradient. So mu into r omega by h is the small shear stress that's acting, and this elemental area is 2 pi r dr. Are you all clear till this point? Yes? So please do respond. Are you all clear till this point? Did you all understand how this dA is equal to 2 pi r times dr? Yes? So please do respond. Yes? Okay, fine. Okay, good. Kapil, Pratik and all. So whoever is online, so please do respond, because it's an online class and I can't see your faces obviously. Okay, so please do respond. Yes, Joshi, correct. So this is your smallest shear force that's acting. Now, can you tell me what is the small torque that will be acting on this disc? Small torque that is acting on this disc. Small torque is nothing but this small force into the radius at which this force is acting, and definitely if this is the elemental area, then this force acts at a distance r, correct? So this implies this is equal to, if you multiply one r in excess, mu times r omega by h into 2 pi r dr into r. This is what we have here, multiply by r, correct? So small r we have multiplied. So now if you write the expression for d tau, means d torque, the small torque is equal to see carefully. Mu times r omega by h, mu times r omega by h into 2 pi r dr into small r. Now, what is the range of this small radius? This small radius varies from the center of axis to the outermost region of the plate. So here, so this small r can vary from 0 to a maximum radius of capital R. Let us suppose the diameter of the disc is capital R. So that we will represent here. You can identify here. So if this is the location and this is the location simultaneously, and if you see this is the diameter of the disc, this is the total diameter d of the disc in general, and d by 2 is, let us suppose, r, capital radius. Okay, so this is the case. Then to get the total torque that is acting on the disc, we can write integral 0 to r mu times r omega by h into 2 pi r dr into r. This is what we have here, correct? So the total torque that is required is equal to, if you do the integration, mu is a constant, omega is a constant, 2 pi is a constant, divided by h is a constant. So if you remove all the constants out of the integration, then you have 1, 2, 3. So there are 3 r's, so which is r cube dr. This is what we have here, correct? So if you expand this, means if you calculate this integration, the total torque that you require means, for example, if you are rotating this disc with the angular velocity of omega, then you will be need of some torque to overcome this friction effects. So the total torque that you need to overcome this friction effects is given by this expression. So which is pi mu omega into 2 divided by h into, if you integrate this, you know definitely integration of r cube dr will be r power 4. So within the limit 0 to r, this is nothing but r power 4 divided by 4. Okay, so this 2 and 4 get cancelled twice, and this expression can be written as pi mu omega r power 4 divided by pi mu omega r power 4 divided by 2 times of h, correct? And of course, if you write this in terms of diameters, this is equal to pi mu omega, and in place of r you can write d. So d power 4 divided by, when you are writing in terms of d, you will have 2 power 4 in the denominator. So 16 into 2 will give you 32h. Okay, so this is the total torque that you require to rotate this disc at an angular velocity of omega, and this is a simple analysis actually. So small shear stress that's act on this, basically this elemental area, and this elemental area is given by 2 pi r times dr. So this is your torque, elemental torque that's acting, and if you integrate the expression, this is a simple term. So the torque required, let us highlight this in a box. So the torque required T is equal to pi mu omega d power 4 by 32 times clearance. This is what we have here, correct? So let us highlight this in a box. Okay, so are you all clear till here? Because this torque is asked in few examinations, so that's why I have deduced an expression for torque. I am identifying how to, what's the amount of torque that you need to rotate this disc whenever this is in contact with some viscous fluid. Is that clear to all of you? Did you all understand how did we get pi mu omega d power 4 by 32h? Yes or no? So please do respond. Can you all understand this? How this happened? And here can you understand why you are using integration? Because the points of solid and fluid contact are not at a fixed distance from reference. Okay, so that's why we are performing this integration. Clear? Yes, very good. Ashwin, Kapil, Shubha, Tangai Velan, Indu, Suyanda, Shubham and all. Fine. So this is your torque. Now, can you tell me what is the power required to rotate this? What is the power consumed in this viscous fluid? Power consumed in overcoming this viscous fluid? It's a simple formula, yeah. There are 4 terms in the numerator, pi mu omega d power 4 divided by 32h. Okay, fine. There is one more thing. What is the power required to overcome this viscous effects? So power is nothing but, let us write this, power is nothing but torque into omega, correct? And this is your total torque, and omega is just a constant anyway. If you take at any point, the angular velocity will be same, but depending upon the radius, the linear velocity varies, correct? So power is nothing but torque into omega. So if you multiply this expression with omega, that's it, pi mu omega square d power 4 divided by 32h. Okay, this is what you will be having. Clear? Okay. Fine. So these are the expressions for power and torque. Okay. Yeah, 2 pi n into T divided by 60 is nothing but tau into omega, and that's what your power. So are you all clear with this? Yes, because this torque required to rotate this disc is being asked in few exams, so that's why whenever this capital diameter of the disc is d, and of course d by 2 can be written as r, in this analysis you will get the final torque is nothing but pi mu omega d power 4 divided by 32 times of this clearance h. Okay, clear? Very good. And also this power required is something like this. Now I'll ask you one thing, you please respond. Okay, so see carefully. Of course, in this analysis, we have neglected this edge effects because there will be some viscous oil that is in contact with this edge. But of course, compared to the length of the disc, the thickness of the disc will be very small. So the area exposed to the viscous fluid will be very small as compared to this particular area. So we are neglecting side effects. Now, I'll tell you one thing. You please tell to answer the cases. Okay. So see carefully. Fine. So see here. Let us suppose there is one disc again, some disc of some thickness, and let us suppose this time. Let us suppose there is a chamber in which this disc is located. Fine. Okay. And let us suppose there is completely filled with viscous oil. This is completely filled with viscous oil. Okay. Let us suppose this is completely filled with viscous oil. This is completely filled with this viscous oil, because I told you that I'll be covering the topics of a bit of ESC as well. So I am giving you all these things because these are quite common, because you know generally every year ESC prelims happens in January, but because of the COVID it got postponed to July this year or June maybe, depending upon the UPSC calendar. So you have some good time to put your focus on all these things. Okay, so I am giving you all these things, so please don't miss out. Okay, clear? So let us suppose there is some viscous oil that is here. And of course, let us suppose the thickness of the disc is too small. Okay, if the thickness of the disc is too small, and let us suppose, you know, this is the axis of the disc, maybe. Fine, this is the axis of the disc, and let us suppose you have small handle which thickness is neglected when compared to the thickness of the disc, so that you are rotating this disc in a angular velocity omega by applying some torque. And let us suppose this complete is filled with viscous oil. Okay, same viscous oil. Okay, so now in this case, of course, you can see the thickness of the disc is very small. So if the thickness of the disc is very small as compared to the diameter d, let us try to identify that as well. So okay, so let us try to identify that. So if this is your diameter of the disc, okay, so let us suppose if this is your diameter d, and again the disc is rotating at some angular velocity omega, and again this clearance which you have on both the sides, this clearance is nothing but h. Okay, so this is one h and this is one h, and this t is the small thickness of the disc. So in this case, whenever disc, and generally if this is the thickness of the disc and this edge area is very small as compared to this total area exposed to the fluid on lateral sides, I mean on the top and bottom faces. Now you have this knowledge on, give me a minute first, let us delete this. So see here, so if in this case when there is viscous oil on one side of the fluid, you have obtained these expressions like tau is equal to, h is same in both the cases. T is equal to, means actually this torque acting is equal to pi mu omega d power 4 by 32h. So now in this case, can you tell me what is the torque that is required in this case? Whenever you know the analysis, when the case is single, means if there is viscous fluid only on one side of the disc, you have seen this is pi mu omega d power 4 divided by 32h. Now whenever there is oil on both sides of the disc, can you tell me what happens? The analysis remains same, but of course the friction gets doubled. Correct? Yes or no? Clear? Yes, disc diameter is d. Okay, I got your point. Okay, I got your I understood your idea that you're trying to tell me. Here we have plotted a bit. Now this should be something like this. Yes, correct. That's what you're trying to tell me. I understood. This is correct now. Disk diameter. This is D. Fine. Okay. So area is double generally. So in this case, if you're having this torque as pi mu omega d power 4 by 32h when the clearance is h, and similarly the clearance on this side is also h, then in this case the torque is nothing but it gets doubled. So pi mu omega d power 4 divided by 16 times of h. Similarly, what could be the power? P is equal to pi mu omega square d power 4 divided by 16 times of h. These are the two formulas that will give you the idea on how much torque you need to apply and also how much power you need to apply, because how much power gets absorbed because of this viscous effects, because the area is doubled and whatever the analysis is on the bottom, the same is for the top as well. Okay, so and for our understanding, let us write one more thing here, that this is a fixed sleeve that in which this shaft is rotated, means in which this disc is rotating basically. Fine. Okay, so this is the case and all the values get doubled, because we have seen in case of a single sided disc, means if in case of a single side oil contact, these are the values, so they get doubled. Correct? This is what you have identified. Now we'll move on to one very important topic, which is the compressibility of fluids. Okay, so this topic is a bit important as far as fluids are concerned in real analysis. So let us go for one important topic, which is compressibility of fluids. Compressibility of fluids. Now tell me what is compressibility of fluids. Tell me what is compressibility. Means what does compressibility of a fluid tells us? What does, if I tell you the compressibility value of a fluid is this much, what is that value? What's the physical meaning that the value gives us? Anyone? So please tell me, if I tell you that the compressibility value of a fluid is this much, so please tell me what is the physical meaning of that value. What is compressibility in general? Density varies. Okay. Pressure applied on that fluid, yes, it's applied. Ability of being compressed, correct. So basically your compressibility tells us compressibility is the measure of compressibleness of a substance. Compressibleness of a substance. Compressibility of a substance. So means basically if you apply certain pressure change on any fluid, by what volume or by what amount the fluid gets compressed. Correct? This is the case. So for defining compressibility, we have some value which is denoted by K, which is called the compressibility of the fluid. This K gives us the quantitative analysis on how much a fluid can be compressed. Okay, so compressibility of a fluid, it is denoted by K, and this K is denoted by the volumetric strain that occurs in a fluid when you apply a pressure difference dP on the fluid. Okay, so K is nothing but, compressibility is nothing but the volumetric strain that occurs inside a fluid or within the fluid whenever that fluid is subjected to some change in pressure. This is the value of some compressible fluid. Okay, I mean compressibility of a fluid, and there is something called bulk modulus. Bulk modulus, and what does this bulk modulus tells us? This is basically some inverse of compressibility, and this tells us, if you write mathematically, this is nothing but minus dP divided by dV by V, and of course this tells us to create a volumetric strain in a fluid, what is the amount of pressure you need to apply. So this is dP divided by dV by V, and this minus sign is a compensation that if your pressure change is positive, means if you are applying more and more pressure, the volume gets decreased, correct? Because it's quite obvious, if you are trying to increase the pressure on a solid or in a fluid, generally in any of the fluids, then definitely the volume tries to be very short, the volume tries to shrink actually. So this is dP divided by dV by V, and this minus sign is the counter effect of, because of this counter effect of these two parameters, pressure and volume. You know, if pressure increases, the volume tries to decrease, correct? So this is the value. Now let us perform some analysis. Let us suppose you have some mass of fluid. Look, let us suppose I am taking 1 liter of fluid and if I am compressing, then will the mass of the fluid get changed? Please respond. If I am taking 1 liter of fluid initially, which has some particular density, and if I am trying to compress this fluid, will the mass of the fluid change? Will the mass of the fluid change? So please do respond. If we are taking some mass of fluid and if you are trying to compress or maybe expansion, let's suppose you are heating that, and if the fluid is getting expanded a bit, then will the mass changes? No. So mass is constant. So you know that mass is written as density into volume, correct? So density into volume, you know this. So this implies if mass is constant, then the derivative of mass is equal to derivative of density into volume. This is what you have here, correct? So this implies derivative of mass is constant because mass is a constant, derivative of mass is 0 because mass is a constant. Yes, all of you are correct. So please see here, if mass is constant, if density of mass, differentiation of mass is equal to 0, if you differentiate this is product of two functions and both are changing. So rho into dV plus V into dO, this is equal to 0. So this implies rho dV is equal to minus VdP, VdO. So this implies minus dV by V is equal to dO divided by rho, means the volumetric strain that's actually happening in a fluid is equal to the fractional change of density, correct? This is the analysis that we know from this mass. Now if you take your bulk modulus, this bulk modulus is nothing but minus, you can see clearly we have written here, bulk modulus is nothing but 1 by compressibility, so minus dP divided by dV by V. This is what we have. So if you substitute this minus of dV by V with this dO divided by rho, then you can write this as minus dP divided by, in place of dV by V, we can write minus of dO divided by rho. Okay, so this is equal to dP divided by dO divided by rho. This is one important thing, and this bulk modulus in general is denoted by the value, denoted by the letter capital E. So generally you write E is equal to dP divided by dO by rho. Okay, and generally this equation is written as dP by E is equal to dO by rho, and this is the compressibility equation that tells us many parameters depending upon the value of E. Okay, so are you all clear till here? Can you all understand how bulk modulus can be related in this particular equation? Like bulk modulus is relating to some change in density of the fluid? Yes or no? So what does bulk modulus basically tells us? To create a unit volumetric strain in the fluid, what is the pressure difference that you need to apply on that particular fluid? This is what bulk modulus tells us. And of course, if bulk modulus is high, then the compressibility of the fluid is difficult. Actually, the compressing the fluid becomes difficult, correct? How is mass constant, sir? Because if I take some 1 kg of water and if I start compressing in a box, then definitely the mass can't go out or mass can't come in, because mass can be neither created nor destroyed. So if I'm doing the analysis in a closed system, then definitely the mass has to remain constant. Okay, fine. So did you all understand how this Young's modulus can be related to change in density of the fluid? Yes. So are you all clear till here? Yes. So all of you, please respond. Yes. Very good. So now I want to tell you one thing. Normally if you take water, this bulk modulus of water at STP conditions, of course, standard temperature and pressure conditions, do you know how much is the value? This is 2 times 10 power 6 kilonewton per meter square. Kilonewton per meter square. And this value of pressure is a very high pressure actually. Normally in second chapter in fluid statics, we come to know that the height of the water column which is required to create this pressure is 20 kilometers height. You know, generally our submarines and all, they travel even in some advanced cases, they travel something in between 350 to 500 meters depth. Okay, but this pressure can be created by a water column which is at a height of 20 kilometers. Okay, so imagine the pressure that's acting on the solid which is under a fluid column or a water column of 20 kilometers. It's a tremendous pressure. Okay, so that's why practically we treat these liquids as incompressible, and of course if you talk about water in particular, compressing water is really difficult. Okay, so that's why if we want, generally we deal with steam and all in high temperature applications, but not with water generally. Okay, so 2 into 10 power 6 kilonewton per meter square. And if you take air value at STP, this is around 101 kilonewton per meter square. 101 kilonewton per meter square. So one thing is very clear from this definition. This bulk modulus is nothing but the pressure difference that you need to apply on a fluid to create volumetric strain, correct? So to create 1 unit volumetric strain, the pressure that you need to apply, the pressure change that you need to create on the inside the fluid is 2 into 10 power 6 kilonewton per meter square, and of course for air 101 kilonewton per meter square. This is a bit easy as compared to STP, means standard temperature and pressure in the, so generally standard pressure is 1 atmospheric pressure and standard temperature is 25 degrees Celsius. Okay, and in some references they take it as 20. Fine. So is that clear? Okay, so are you all clear till this moment? So that's why you can see clearly, if Young's modulus, this bulk modulus of air is small, that means compressibility is nothing but 1 by bulk modulus. So compressibility of this air is high because this value is less. But whereas in case of water, this bulk modulus is very high, which means your compressibility is 1 by K, which means 1 by this value will be very low. So compressibility is very low. That means compressing water is practically very difficult. Is that clear to all of you? Is that clear to all of you? Yes? Okay, fine. Now we'll move to one particular topic, which is incompressible versus compressible flow. Because since we are talking about compressibility, so we can write this at this stage: incompressible versus compressible flow. So what is this incompressible versus compressible flow? Look, fluid can be incompressible, but sometimes we analyze the flows to be compressible or incompressible. We'll see. Compressibility of fluids and incompressibility of fluids is dependent upon this Young's modulus of water, and straight away the compressibility of any substance is nothing but 1 by this Young's modulus. So we can just write depending upon these values. But sometimes the flows can also be compressible. How? We'll see. Look here. Let us suppose there is some pipeline that's carrying some fluid maybe. Let us suppose this is P1 pressure, and let us suppose here the pressure is P2. Okay, and definitely there will be some pressure drop in actual cases. Whenever a fluid is flowing, there will be some pressure drop in actual cases because of the friction between the pipe and the fluid, correct? You know this? Normally in practical applications, of course, which we deal in much detail when we deal the topics flow through pipes and viscous flows of incompressible flows, but viscous flow of incompressible fluids. But normally in a pipeline, if you take there is some flow of fluid, then definitely within a given length L, there will be some pressure drop, which you later come to know that there will be some pressure gradient in the horizontal direction. Clear? So when this pressure drop is happening, then depending upon the values of this P1 and P2, means basically depending upon this difference in the values of P1 and P2, the flow may suffer some compressibleness in it. Okay, so how do we quantify this compressibleness of a flow? Look, later in the 4th chapter when we are dealing with fluid dynamics, we come to know that in a fluid flow, the order of the pressure difference, this will be in the order of half times rho v square, where rho is the density of the fluid that's flowing in and v is the average velocity. Okay, so we come to know in 4th chapter in Bernoulli's equation and all, generally the order of this pressure change from P1 to P2 will be in the order of magnitude half into rho v square. Okay, so are you clear till this point? First of all, did you understand why there comes certain pressure difference in a fluid when a fluid is passing through a pipe? Yes, can you understand this? Can you all understand? Whenever there is some fluid that is passing through a pipe, definitely this P1 gets dropped because of the friction between the pipe and the fluid and also some other losses. Yes or no? Can you understand that this P1 and P2 won't be the same generally in actual cases when you take friction into consideration? Yes, yes, whatever. What is the name of the loss? We'll name it later, but for the time being, can you all understand that there is some loss in the energy of the fluid because of the friction, and this P1 and P2 will not be the same. So P2 will be a bit less than P1, correct? There is some pressure gradient. Now, in Bernoulli's equations and all, of course, in the fourth chapter, we come to know in later stages that this order of this pressure difference means the change in this pressure P1 and P2 is directly in the order of half times rho v square, where rho is the density of the fluid that's flowing and v is the average velocity of the flow. Now, let me make some analysis clear here. So, this implies order of dP by bulk modulus. This will be same as order of half into rho v square divided by E. Just I am dividing with bulk modulus of the fluid on both sides. Okay, I am dividing with bulk modulus of the fluid on both sides of this equation. Now, if you go to previous slide a bit, this dP by E, look, this dP by E can be written as dO divided by O, correct? So, from bulk modulus analysis, whenever this mass of the fluid is constant, at the end, continuity equation has to be satisfied, means whatever the mass that's flowing in, definitely that should come out, because the pipe is under steady state operation and definitely there can't be any mass accumulation within the pipe. Whenever there is no mass accumulation within the pipe, whatever the mass that's going in, that should definitely come out. Then what happens? Whenever your mass is constant, your change in pressure divided by the bulk modulus of the fluid, this should be equal to dO divided by rho, correct? So here in place of dP divided by E, I am writing dO divided by rho, and this is approximated to half V square divided by E by rho, correct? Now, what is this term E by rho represents us practically? If you take any fluid, then this E by rho represents the acoustic velocity. Means generally, if in a fluid, what is the velocity of a sound wave is given by this bulk modulus divided by rho, which of course I will derive and I will show you in the 11th chapter, in the 12th chapter, basics of compressible flow. Okay, that deals a bit of compressible mechanics, and we need to derive this equation. So basically, this E by rho means square root of this E by rho is nothing but A, and this A is nothing but acoustic velocity, means the velocity of the sound wave within this medium. Means if you try to pass a sound wave within this medium, then what is this velocity? That's given by acoustic velocity. Okay, so this is your acoustic velocity, and which means, can I write this order of change in density of the fluid is equal to order of half into V square divided by A square, or can I write V by A whole square? Yes or no? Can I write this? Are you all clear till here? Just look, it's a simple analysis. The first thing that we have taken is the order of the pressure difference that's happening in this flow is equal to order of half into rho v square, and we have divided both the terms with Young's modulus, this bulk modulus, and once we have divided with bulk modulus, from previous slide we know this dP by E for any fluid means the pressure difference divided by the Young's modulus, pressure difference divided by the bulk modulus is equal to dO by O. So this is equal to half into V square by E by O. And from compressible mechanics, we know that this square root of E by O is nothing but the acoustic velocity of the fluid. So we are writing this as half into V by A whole square. Are you all clear till this point? Are you all clear till this point? Yes? So please tell me, are you all clear till this point? Why we use order of? Because exact magnitudes won't be equal, but if this is of range 10 power 5, this will also be in the range of 10 power 5. Okay? So that's why we use just order but not exactly magnitudes. Clear? So if this is the case, now can you tell me your actual velocity divided by acoustic velocity divided by acoustic velocity, your actual velocity divided by acoustic velocity, which is V by A. V by A. This term is called, can anyone tell me, can anyone in the class please tell me this actual velocity of the flow divided by the acoustic velocity in that medium, this ratio V by A is called, this is called one dimensionless number, because this is also velocity, this is also velocity, so this ratio is called Mach number. Okay, and generally have you seen Mission Mangal, any one of you? Mission Mangal is a recent movie on launching Mars mission. Have you seen Mission Mangal movie, any one of you? Yeah, this is Mach number. Okay, that is fine, which is denoted by this MA, Mach number. Fine. No, you haven't seen Mission Mangal movie. Yes. So in that movie, they will be telling Mach scale crossing 2, 3, 4, which means what is that? Actually, this actual velocity is more than 3 times of acoustic velocity, 4 times of acoustic velocity. This is what they mean when they say, which language, sir? Hindi? Mission Mangal is Hindi movie actually. Fine. So this is your Mach number, correct? So this is your Mach number. So if this is your Mach number, so see carefully, which means your order of change in density is depending upon order of half Mach square, Mach number square, correct? This is your Mach number square. So let us write this point, which means whenever any flow is happening, the rate at which this means the magnitudes of this pressure, this densities variation is of the order half times of Mach square. Now, which means one thing is very clear, if you are having some flow that's happening, then definitely if this is your P1 and P2 generally, and if the density here is O1 and O2, of course, then this order of fractional change in density O of dO by O, this is of order half Mach square. Now, when you assume a fluid to be incompressible, or when do you assume a fluid to be compressible? Look carefully, I will be telling you. If this density variation is less than 5%, means throughout the flow, because of the friction, there will be pressure drop. That's quite common. But because of the pressure drop, because of the friction, there is some pressure drop, and of course, there is some change in the density of the fluid, correct? But if the change in density of the fluid is less than 5%, if the fractional change in the density is less than 5%, then we treat this flow as incompressible flow, because the density variations are not more than 5%. Are you all clear? In engineering applications, we treat that this dO by O is less than 5% for any incompressible flow. Are you all clear till here? Are you all clear till here? If this density variation, because of this factors involved, is less than 5%, then we treat this flow as incompressible flow, correct? Yes or no? Now, please see carefully. If this value is less than 5%, which means if this value is less than 5%, if this is in percent, that means dO by O is less than 0.05, correct? Because 5 divided by 100 in case of this. dO divided by O is less than 0.05, so this is less than 5%. So if you consider this 0.05 is equal to half times Mach square, then what will be the Mach number? Or you can write maybe, fine, let us suppose if this is greater than this, then Mach number is less than square root of 2 times of 0.05. Let us calculate this value, which is actually square root of 0.1. So let us calculate this using a virtual calculator. Let us calculate this. Gate calculator. So this is the gate calculator, of course, which you will be seeing in your gate examination, and whenever I solve some PYQs or any other questions, definitely I'll use this calculator and I'll perform the calculations along with you. Okay, so you please make your pen and notebook with you, and you please make your calculations along with me. So 0.1 square root, we can type here, so 0.31622. So you can see, if you round off to one decimal generally, this Mach number is less than 0.3. Okay, so 0.316. So generally, if you round off, you come to 0.32, 0.32, or some books they just round it off to single decimal place, which is 0.3. Okay, so which is if you round off to 2 decimals in general, 0.316, and so 0.32. So this is your limitation for the Mach number, for calling the flow to be incompressible. Flow to be incompressible. Okay, which is 0.05. In ESC prelims has which calculator? In ESC prelims, first of all, no calculator is allowed. Okay, you need to make all your calculations on your own. For ISO exam and for ESC prelims, there is no calculator allowed. Okay, so you need to make your calculations on your own. Fine. Look, so whenever if there is some flow which is happening with a velocity such that the Mach number of the flow will be less than 0.32, then you can generally assume that flow to be incompressible. Means the density variations that's occurring here will definitely negligible. Yes, incompressible flow and fluid. I am telling you many times, an incompressible fluid can suffer a compressible flow generally. Okay, so this can happen because if I am telling the fluid is incompressible, that means I just mean the bulk modulus value. That's it. If my bulk modulus value is high, then the compressibility is low. And if my bulk modulus is a bit low as compared, then compressibility is high. So, but in compared to flow, this completely depends upon this Mach number and the velocities that are flowing here. Okay, so definitely an incompressible fluid can suffer a compressible flow, and similarly a compressible flow can also suffer, compressible fluid can also suffer an incompressible flow. Okay, no issues. So for any Mach number less than 0.32, this flow can be treated as incompressible, and for Mach more than 0.32, generally when it is more than 1/3, we consider this flows to be compressible. Flow to be compressible. So are you all clearly understanding the difference between incompressible fluid and incompressible flow? Many times an incompressible fluid can suffer a compressible flow depending upon the pressure loss. At the same time, compressible fluid can also suffer an incompressible flow if it's flowing at a bit of low velocity. Is that clear to all of you? Is that 2 points clear to you? Can you all clearly distinguish between incompressible fluid and incompressible flow? Yes or no? So please respond. Please do type in the chat box. Can you all identify the difference? Young, compressibility of a fluid is decided only by the bulk modulus of the fluid, but compressibleness of a flow is decided by the Mach number. Okay, fine. So this compressibleness or incompressibleness of a flow, it depends upon quite this Mach number, which is less than 0.32, the flow is said to be incompressible, and of course if the bulk modulus is if the Mach number is more than 0.32, then we call the flow to be compressible. Generally if you take air, so generally velocity, acoustic velocity in air is around 345 meters per second, 347 meters per second and all as per standard values, but of course if you put this acoustic velocity A is equal to 347 and Mach number is equal to 0.33, then you will get the velocity limitation at maximum at which your fluid can be treated as incompressible for your analysis. Okay, so this is what I want to talk about incompressible flows and compressible flows for today. Is that clear to all of you? Yes. So, did you all understand all the topics that we have discussed today? Basically, we talked about certain two cases of Newton's laws of viscosity. Basically, this wedge, a block sliding on a wedge, and also one more case, like basically a circular disc rotating on a layer of fluid. This is what we have seen, and also we have seen the definitions of compressibility and incompressibility of fluids, and thereafter compressibility and incompressibility of flows. Okay. So this is basically the difference, how you will identify incompressible versus compressible flows in general. Okay. Now I want to give you one extra thing at this point. Look, fine. In compressibilities which we talked, compressibility of a fluid, which is K, denoted by K, which we have seen today. When the live session started, it started on 9:30. It started at 9:30. Effect of temperature on K. Normally, you see there is a little bit volumetric expansion of liquids in general, but of course, gases do suffer, as you are telling. Effect of temperature on K, gases do suffer some, compression. Of course, some variation in densities basically when they are subjected to some temperature. Okay. Okay, yeah, subsonic, sonic and supersonic, they depend upon the Mach number. Generally, any flows that happen beyond Mach number, means less than Mach number, are called, they are called subsonic flows, and fluids or the flows which are happening at some speed which is equal to Mach of 1 are called sonic flows, and the fluids or the flows which are happening more than Mach number 1 are called, supersonic flows in general. Okay, Vienna? Any interview question, that's what they ask you. What is the difference between incompressible fluid and incompressible flow? This is the main question. Okay. If you can understand the difference very well, Rahul, then definitely you will get to the interview. Okay, because many of you discuss this generally. Okay. They'll ask you, can any incompressible fluid go under a compressible flow? If you say no, that's it. Your answer is done. Okay. Fine. So let us talk about this compressibility of a fluid. Let's get back to the compressibility of a fluid. So K is given by minus dV by V upon dP, and generally we write this as K is equal to minus 1 by V into dV by dP. Okay, and of course practically liquids are not compressible, means they are basically incompressible, but coming to gases they are a bit compressible. So let us see some certain cases of gases actually. So let us see there are two types of thermal compressibilities. One is the isothermal compressibility. For gases I am dealing. For gases there are two types of compressibility, which is the isothermal compressibility, means during your compression process you maintain your temperature to be a constant. Okay, so isothermal compressibility. What does this isothermal compressibility tells us? This is denoted by KT, and this T generally in isothermal process temperature is constant, so this is denoted with K with the subscript of T. And in fluids we generally deal with liquids and gases, but practically liquids are incompressible but gases are a bit compressible, so they have certain characteristics. This KT is nothing but minus 1 by V into dV by dP, but of course at constant temperature. Now please tell me, if we are dealing with a gas, and let us suppose we are using some ideal gas analysis, means if the gas is assuming or showing ideal behavior, if the gas is showing ideal gas behavior, then you know that the ideal gas equation is given by PV is equal to mRT. You know this. Correct? You know this. So this implies V is equal to mRT divided by P. You know this, correct? So mRT divided by P. So now let us try to understand something here. And your isothermal compressibility KT is nothing but minus 1 by V into dV by dP at T. So if this is the case, your KT is equal to minus 1 by V into, look, if you are dealing with isothermal case, that means your temperature is constant or not constant. If you are dealing with isothermal case, then temperature is constant or not constant. Yes or no? So please tell me, if you are dealing with isothermal case, the temperature is constant or it's not constant? It is? All of you. If you are dealing with an isothermal case, the temperature is constant? Yes, it is constant. Correct. So if temperature is constant, then if I am differentiating this with respect to P, then instead of this dV by dP, for any gas this mass is constant. Of course, since the compression can be done only in closed systems, so m is constant. This characteristic gas constant, which is universal gas constant divided by the molecular weight, is also a constant, because once gas is fixed, your universal gas constant is fixed and also your molecular weight is fixed. So mR is a constant, and because of this isothermal compression you are assuming this T also a constant. So mRT divided by differentiation of 1 by P is nothing but minus 1 by P square, minus 1 divided by P square. This is what you have. So which means here we can write minus mRT divided by P square. Correct? So this minus and minus gets cancelled off. So this minus and minus gets minus into minus, it's basically plus 1. So this is equal to mRT divided by P square into V, of course, Vp square, because there is one V. So as per ideal gas equation, you have PV is equal to mRT, which means I can cancel this mRT, I can cancel this V and also one P. So which is left here is 1 by P. Okay, and of course in ideal gases we substitute absolute pressures. So definitely the isothermal compressibility of any gas in general of an ideal gas is equal to 1 by absolute pressure. Okay. Fine. Is that clear to all of you? KT of an ideal gas is 1 by P. Is that clear? Yes or no? Sometimes they ask you this for ideal gases, generally what is this isothermal compressibility? So isothermal compressibility of ideal gas is nothing but 1 by absolute pressure P. Is that clear to all of you? Yes? Okay. Sometimes the compression process happens very fast in general. So in such cases, we talk about one more particular term which is called the adiabatic compressibility. Okay. So we talked about adiabatic compressibility. Okay, and what does this adiabatic compressibility is defined by? So normally any compressibility is given by this formula minus 1 by V into dV by dP. So minus 1 by V into dV by dP, of course, at constant S. So generally this reversible process and adiabatic process is termed as isentropic, of course, which you see in thermodynamics. That's a separate course, and for which you can the complete course of basic thermodynamics is also available on this YouTube channel of Engineers Hub. Okay, so you can find that's also done by me. So you can just go to the basic thermodynamics course once for a while if you are free. So this is the definition of this adiabatic compressibility of any gas. Okay, and of course in ideal cases, and if the gas is going and if the gas is going adiabatic process in ideal gas, this is given by PV power gamma is equal to constant. So similarly, you can deduce the relation between dV by dP here. Okay, in this case, if you try to deduce that, P into gamma into V power gamma minus 1 into dV plus V power gamma into dP is equal to 0, and you can cancel this V power gamma, then there comes a V here. So you can write what is dP by dV from this gamma into P by V into dV is equal to minus dP, and of course your dP by dV or dV by dP, maybe this is equal to minus V by gamma P. Okay, so you can see here minus 1 by gamma P generally. So if you substitute there, minus 1 by V into V gets cancelled, so 1 by gamma times of P will be your adiabatic compressibility of a gas, ideal gas, of course. I have already taught thermodynamics, Rahul. That's available in the, I'll show you. Just please give me 5 minutes. Anyhow, we are going to end this lecture. So let us, if you see carefully, let us, this lectures could do a best purpose if they are present here. Okay. Similarly, this can also be moved here. Okay. Fine. So these are compressibilities of the fluids, and in compressibility of fluids, you can just see all the isothermal compressibility and adiabatic compressibility as well. Okay, so this is how what you can see. So are you all clear with today's lecture? Are you all clear with today's lecture? Have you all understood what is this compressibility? What is this Newton's? See, basically let us go for the initial case. We have started with the case of a block sliding on an inclined plane, and of course we have found an expression for the terminal velocity V. Next, if you see, this is a disc that is rotating on a layer of viscous oil, and we have seen what is the expression for the torque that is required to create this rotation or to maintain this rotation. Similarly, thereafter power, and also we have extended our analysis whenever the disc is surrounded by the fluid completely, means if you have two layers of fluid, means two fluids on both the sides, then what is the torque that is required. Similarly, we have moved into the compressibility of fluids. So compressibility is given by this value which is here. Actually, you can see this minus of dV by V divided by dP is compressibility, and this compressibility is a measure of compressibleness of a substance in general. Okay, and this bulk modulus is actually reverse of compressibility, so 1 by K, and this is nothing but minus dP divided by dV by V. So we have seen different compressibilities like isothermal compressibility, and for ideal gas we have seen that the isothermal compressibility is equal to 1 by absolute pressure, and also we have seen the case of adiabatic compressibility. Okay, so once we have seen that, we have seen some directions when mass is constant, this volumetric strain, negative of this volumetric strain can be written as fractional change in its density. So dP by E is equal to dO by O. That's what we have discussed, and of course we have seen the values of bulk modulus of water at STP and bulk modulus of air at STP. It's obvious bulk modulus of water is high, 2 into 10 power 6 kilonewton per meter square, which means your compressibility value is very less. 1 by this value is very less, so which means water is practically incompressible. Okay, so that's what we can identify here, and also for air the value is just 101. So as compared to 2 into 10 power 6, this 101 is very small. So air is generally 2 into 10 power 4 times more compressible than water. That's what we can say from these values. So finally we have done some analysis to identify how to identify whether a flow is compressible or incompressible. So we have seen the difference clearly between incompressible fluid and incompressible flow. Correct? I hope we are all clear till this point, and also we have given some condition finally, so that beyond this condition, this is the limiting condition to assume a flow to be compressible or incompressible based on our engineering approximation, that this density less than 5% can be treated as an incompressible flow. So this is the definition of, this is the mathematically limiting condition for the flow to be an incompressible flow, and of course this is a compressible flow whenever your Mach number is getting more than 0.32. Are you all clear till here? So if you are all clear till here, then I would like to show you some important links that are available here. Look, if you go to the official YouTube channel of Engineers Hub, you know in YouTube, if you just search Engineers Hub, this is a official channel of Engineers Hub, which you can see here. So in this we have job notifications. So you can see clearly there are pretty much job notifications that are being launched within past 2-3 days. So we have done some good content related to the dates, the important dates, and also what are the eligible criteria for applying for different jobs and all. So this is the complete playlist where you can find the job notifications of all. Okay, there are much more videos to which you can see, and all these other videos that are available for us. So you can HPCL recruitment without GATE, and majority many of the companies they are recruiting without GATE. So even if your GATE 2021 is not that well, please don't get disheartened. You can just keep on preparing for the other exams. Next, this is the engineering mathematics course that's done by me, which many of you know, because first of all we both met because of this engineering mathematics. So this is the comprehensive course which includes 46 lectures that we have done during the lockdown time, and that showed you have already shown a great love for that. And this is the revision and GATE PYQ series of engineering mathematics, where we have solved more than 700 problems of engineering mathematics related to GATE 2021. And almost, if you check the GATE 2021 papers and also this playlist, then almost some 75 to 80% of the questions are again from this playlist. And also GATE ESC Mechanical Engineering, this is the fluid mechanics playlist which is going on, and of course this has 4 lectures because already 4 classes are stranger man dangers, please my name announce. Okay, I announced. Okay, fine. Anyhow, so this is the basic thermodynamics course which you can see here. Okay, so this is basically this basic thermodynamics course. Of course, here you can find, and also you can find some lectures of heat transfer as well, and of course some GATE 2020 detailed solutions. But of course, these are the 2 playlists that gives you the complete analysis of, one about fluid mechanics and another about basic thermodynamics. This basic thermodynamics is also done by me, so you can just go through the things. Okay, and also for all latest updates, please go to this job notifications, and on, as I was telling you, upcoming live streams you can see on 6th of February at 7 p.m. This, let us go to our slide. So see here, on 6th of February at 7 p.m. you are having this unexplored IIT Bombay session by 2 IIT Bombay alumni, basically this our VS sir and our Negi sir. So they'll be disclosing you how IIT Bombay looks like and what are the facilities and what are the opportunities that are available at IIT Bombay for you. Okay, so it's like disclosing IIT Bombay opportunities. Now coming to our tomorrow's lecture, then we'll discuss, we have already talked about compressibility of fluids in today's lecture because we got enough time, so we are already moving 1 lecture ahead. So definitely in tomorrow's class we'll talk about surface tension and its effects. Okay, so because this compressibility of fluids we have done good enough because of some time that we had today, so in tomorrow's class we'll talk about surface tension and its consequences like capillarity and all other consequences, basically pressure difference inside a bubble and a liquid droplet and all. So please don't miss tomorrow's class. Okay, tomorrow there is slight change in the timings. Tomorrow we'll start the class at 8 o'clock and we'll end that by 9:30. Okay, so please make a note. So tomorrow the class will be at 8 p.m. and the class runs from 8 p.m. to 9:30 p.m. Okay, so 1.5 hour class. So please don't miss that. Okay, because we have some other assignments, so we are just preponing the class a bit. Okay, so on the same place we'll meet again. And of course, so if you want to see that we are starting some batches for offline, so we have started some offline batches, and one batch we have started on 1st of March which is running successfully. So this is the classroom of that batch and things are going fine. So definitely every day we are having the class from 2 p.m. to 7 p.m. and of course this program will be completed within 5 to 6 months. Okay, so meanwhile you'll be having a lot of job notifications and other public sector recruitments without GATE. So please do make use of this opportunity for you. Okay, and also we are going to start a second batch from 15th of March. So 15th of March and finally one last batch on 29th of March. Okay, so yeah, only for tomorrow. The timing change is subjected only for tomorrow but not for the whole course. Okay, only for tomorrow. So tomorrow we have a class at 8 p.m. So please do join live at 8 p.m. Okay, so anyhow, so these are the batch details that we are running, and of course this is the classroom, and so these are the official contacts where you can find some useful content always on this YouTube channel of Engineers Hub, and we are posting the notes on daily basis in this Engineers Hub mechanical channel. Okay, so I hope you are getting the notes daily on this channel, correct? Are you all getting notes on this channel on daily basis? Yes or no? So please tell me, are you all getting the notes on this channel on daily basis? Yes? Yes or no? So please tell me, are you all getting these notes on daily basis on this channel? I personally is posting the notes daily, so you can find the PDF copy of my class notes daily on that Telegram channel, correct? Yes, Sushan, you are getting, so and all of you, good. So anyhow, this is our official website and this is our official Facebook page, My Engineers Hub, and also this is the LinkedIn profile, and this is the official website of Engineers Hub. So we have also launched one app, Infinity, which you can download through the Play Store, and in that app we are planning to conduct some free live classes very soon once the platform is ready. Yeah, you will get some assignments, Pratik, no issue, because I am telling you, in the Infinity app we are posting some daily practice problems, 5 problems a day. Okay, so you can practice that problems, and also we are conducting one weekly test on every Thursday at 7 p.m. Today there is a test which is active, but of course, right, you can't start the exam now anyhow. So that is the case, but questions, yes, definitely we'll solve some questions. On Saturday, we'll have a session for completely solving this PYQs and some good questions on fluid mechanics. Means basically the first chapter, fluids and its properties. Okay, so are you all clear till here? Every week we'll be having one problem solving session, means like a tutorial session where I'll deal all the PYQs that came on the similar topics and also some nice questions on fluid mechanics. So is that clear to all of you? Is that clear to all of you? No, initially we thought 5 days for questions, but of course, if we are taking only 4 active lectures per week, then this course gets extended for many days, like beyond 60 days. So we thought of making 5 lectures per week and also 1 tutorial on Saturday. Okay, because if I take only 4 active classes per week, then this course may get extended beyond 60 days, which could not make the benefit to many others. Okay, so to compress that duration, we have taken this initiative of taking 5 active lectures per day, per week, and also 1 lecture on practicing sessions. When course will complete? Probably by last week of April. Okay, because I need at least 40 to 45 lectures to complete this 12 modules, and every module, let us suppose if it's taking 4 or 5 lectures, then it needs some time. Okay, fine. So yeah, these are the things. So I hope all of you are happy and course is going in a better way. Correct? Is the course going fine to all of you? Please do respond. Please do type in the chat box. Is the course going fine to all of you? Thank you, Mansing. Okay, so please share your. Yeah, thank you. Yeah, I love you too, Mansing. No issue. Okay, fine. So please type your comments in the chat box. Please give your valuable feedback so that if something can be done better, we'll definitely do for that. Okay, and I hope you're getting the concepts in a nice way. Better. Thank you all. Then good night. Have a nice sleep. We'll meet tomorrow sharp at 8 p.m. and the timing change is subjected only for tomorrow. Okay, from Saturday we are having the class again at 9:30 p.m. Okay, so no issues. So we'll meet tomorrow at 9 p.m. Thank you all. Have a nice time. Sushan, you are telling something, sir. Recently I watched your mathematics course. It's really helpful, sir. Content are highly good. Thank you, sir. Okay, you're welcome, Sushan. So definitely this engineer sub is committed towards the betterment of the students, and we'll post much of the content for free on this YouTube channel. Okay, so that many of you will get benefited. Thank you all. Have a nice time.